we've covered the Otto and diesel cycle. We've had the introduction to the Brayton cycle. And now we look to enhancements, common enhancements to the Brayton cycle, regeneration, and then we'll deal with reheat and intercooling all together. But first we'll deal with regeneration. Here's a problem, and the problem is that you have a regenerative gas turbine operates at steady state. Well, what do they mean by regenerative gas turbine? Make a sketch of a traditional turbine. So you have a compressor, then a combustor, or what I'll call a burner, then come out to a turbine, and then you have a heat exchanger in which you close the loop, and that would be the standard Brayton cycle. So state 1, state 2, state 3, and state 4. And then what they notice is the temperature at 4 is quite high. And all you're doing is throwing that out, Q out. So what the goal would be to say, well, why don't I try to use some of this high temperature exhaust gases instead of just disposing it to the atmosphere? Wouldn't it be better to try to heat up some of the gases that would be heated by burning a precious fuel in the burner? So try to heat up from 2 to some other state before it goes into the burner to reduce the amount of heating that's done in the burner. That's the goal of the regenerative gas turbine cycle. So what they do is they say, well, let's reroute. So we'll take the exhaust gases out of the turbine, come up and put them through a heat exchanger. And the heat exchanger, the purpose of that heat exchanger is to preheat the gases before they get into the burner. Now, so what we do is we get rid of down here, get rid of this, get that out of the way. And we still have to close the loop, so we bring it over and come down and then go into the compressor. But before we put it into the compressor, that regenerative heat exchanger doesn't cool it down enough, so you'll still have to have another heat exchanger, just like you did down here, to reject some heat to the ambient atmosphere. So this is Q out. All right, so let's take a look. You still have Q in the burner. You still have Q out for a heat exchanger over here. You still have the work coming out of the turbine, and you still have the work driving the compressor. But this added regenerative heat exchanger, okay, what does it change? Does it change the work of the compressor? No. Does it change the work of the turbine? No, because often this temperature going into the turbine, this T3 is T max. That's your maximum temperature. Don't change your maximum temperature. This regenerative heat exchanger doesn't change the maximum temperature. So it doesn't change WC or WT. What it does is it reduces Q in. Q in is smaller because you're getting it heated up from 2. And now here's the little bit of a challenge. When it comes out of the turbine, they stay with state 4 right here. But they didn't want to reorder the numbering system, leave 1 right here. So what they do in the textbook is they call this state X and this state Y. So it goes from 2 to X before it goes into the burner, and it goes from 4 to Y before it goes to the other heat exchanger to reject the heat. So I'm not in favor of the use of X and Y for states. Usually use states as 1, 2, 3, 4 integer numbers, but here you go, staying consistent with the textbook. Is there any pressure loss in the heat exchanger? No. You do have a high pressure side because it's high pressure at state 2, X, and 3, and the low pressure side, it's low pressure at 1, Y, and 4. But that's a regenerative gas turbine. Let's do this. Let's go ahead and look at it on a temperature entropy diagram. So we have the temperature entropy diagram. We'll start at state 1, go through compression to state 2. And now you have constant pressure heat addition. Okay? And you're going to go up all the way to state 3. Then you would expand down, and that doesn't look too well, does it? I need to put these closer together, sorry. Let me put 1, like that, expand down. So what we see is state 4 is very high temperature. So what we want to do is we want to cool some of the exhaust gases off while heating some of the from state 2 up to state X, and this is cooled down to state Y. Okay. Now, if you have a counterflow heat exchanger, which is common, and you have the hot side on one and the cold side on the other, they're both air in this case. This comes in at state 2. This goes out at state X. This comes in at state 4. This goes out at state Y. You might ask yourself, the temperature at Y is going to be less than the temperature at 4. The hot fluid's going to lose or decrease in temperature. It'll be heat transfer out of the hot fluid into the cold fluid. And the cold fluid is going to heat up. But how high or how low could Y be? And likewise, how high could X be? And a lot of times they'll plot like on a temperature kind of scale X from one side of the heat exchanger to the other side of the heat exchanger. They'll show the cold fluid heating up, going from T2 to TX. And the hot fluid coming down, and because they have the same mass flow rate, those slopes of those lines, assuming constant specific heats, would be exactly the same. They'd be parallel lines. And then this would be T4, and this would be TY. Well, if you make the heat exchanger larger, it's kind of like trying to stretch out the length here. I know this is not going to be a great illustration, but if I wanted to do this, make it longer, and so now I'm bringing in 4 over here and taking out Y over here. I'm bringing in 2 over here and taking out X over here. And if I put my same temperature length diagram from inlet and outlet, so the T2 is not changing on the magnitude, and T4 isn't changing on the magnitude, right? T4, it's the same height. But what you can find is that the slopes will be just like this, and the difference will be becoming smaller and smaller and smaller, delta T. And if you have a short, stubby heat exchanger, not very much area, it'll be a large delta T within the heat exchanger. And this delta T right here, you know, that's what I'm talking about. So theory, the exit temperature for the hot could be as low as T2, the inlet temperature of the cold. And the exit temperature of the cold could be as high as T4, the inlet temperature of the hot. That's a tongue twister, isn't it? Yeah. So what you do is this could go as high as 4. This could go as low as, Y could go as low as 2. So, an ideal situation, that's right. So what we do is you have the efficiency or the effectiveness, this book calls it the effectiveness of that regenerative heat exchanger. They use a symbol like eta, REG. So it's the regenerative heat exchanger effectiveness. And they say, look, the actual amount of transfer, well, you could do it from the perspective of the cold fluid being heated up. It would be going out from H2 to HX. That's how much increase in the enthalpy of the cold fluid. Compared to the maximum increase of the cold fluid, well, it could go as high as H4 on the exit. If you had constant specific heats, it would be Tx minus T2 divided by T4 minus T2. And often this is specified. Maybe it said, oh, it's 80% is the regenerative heat exchanger effectiveness. All right, so there you go. We've now covered the theory to now analyze this problem. So let's take a look at this problem right here, having covered the theory. So what they're saying is the inlet to the compressor is 100 kPa and 300 Kelvin. They're fixing T1 and they're fixing P1. Whoops, P1. The pressure ratio is 11. So P2 divided by P1 is fixed to be 11. The inlet to the turbine is 1400 Kelvin, so this T3 is 1400 Kelvin. This is typical type of information specified. The isentropic efficiency of the compressor and turbine are 100%, so they're reversible. And the regenerator effectiveness is 50%, so they're specifying this eta regenerator to be 50% for this problem. Now they ask, go ahead and determine the thermal efficiency and the backwork ratio. So what I do is, if you assume cold, it doesn't say to assume cold air standard, or use the air tables accounting for variable specific heats. It's your choice. You can go one way or the other. It doesn't appear to be specified in this problem. But you can think of this X is because the 50% effectiveness is being halfway between T2 and T4. Just halfway. Maybe I sketched it showing it's about a 50%. And likewise, Y will be about 50%. In that case, the exit temperature Tx is equal to the exit temperature Ty. But they're coming out at different ends. Okay, because here you're picking up half, it's giving up half of what it could. So let me do this. Let me show you an Excel spreadsheet where this problem's solved. And then I'll walk through it because I think once you've done a few of these calculations, they do become a little tedious. But here we go. So we specify, as I've shown, a little header here. And I'm using variable specific heats. So I specify the pressure ratio is 11. And then I have a little column of, it reminds me how did I determine each of these states? State 1, state 2s, 2, state x, state 3, 3s, 4, and y. All right? Now, the difference between 2s and 2 is a little redundant because the isentropic efficiency of the compressor is 100% and the isentropic efficiency of the turbine is 100%. But all I would need to do is go in here and change it up, and I think I did in another problem. And then I have a new problem, and it would account for it. But let's continue to look at this table of properties. So I have the state numbers, then I have the pressure, and you see it's 1. And you can go through, it just jumps up. Now I have the high pressure. It's 11, the pressure ratio, 11 times 100 kPa, so it's 1100 kPa, and then it jumps back down when you go through the turbine from 3 to 4, back down to 100. Let's take a look at the temperatures. I bolded the information which is given, so the P1 and the T1 are given, as well as T3, the maximum temperature of, whoops, it should be 1450 right here to be consistent with Excel. But you can see how I go from this state 1 to 2s. Using the air tables, you look up the PR, then you recall PR at 2 divided by PR at 1 is equal to the actual pressure 2 divided by the actual pressure 1. You do know the pressure ratio. You looked up PR1, and now you calculate PR2 is just 11 times PR1. And there you go right there. Okay. Using PR, really what we said is I know the pressure and its isentropic expansion, or not expansion, compression through the compressor. Now I can look up H as well as T. Then I say, okay, now that I know these H's, what is the isentropic work of the compressor? It's the difference between these two H's, is it not? So it's 595.8 minus 300.12. It's around 296 kilojoules per kilogram. If I had anything but 100%, but because it's 100%, the actual work is still 296. And so I would then update to get the enthalpy at state 2, knowing the actual work. But these enthalpies are the same. Okay. Now I jump all the way. I forget about X for a minute. I'll come back to it. Go to 3 because state 3 is fixed. You're told that it's 1450 Kelvin. You can look up H as well as PR. Then you divide by the pressure ratio as you go from 3 to 4S. And so it's 522 divided by 11, you have 47.5. Use that to look up H and T if you want to look at it. You don't really need it. You really need the H's. 4. Get the work of the turbine isentropic. That would be right here. 755. It's the same. The actual work is the same because its efficiency is 100%, and so the actual exit enthalpy at 4 is the same as 4S. And now I know how hot it is. Look at it. It's coming out 800 degrees. And when it's coming in, it's a little below 600 degrees. So before I burn the precious fuel to bring it up to 1450, why don't I try and bring up the temperature using that regenerative heat exchanger as much as possible? So what we do is we say the delta H right here is the maximum, true, because it's the regenerator, the maximum Q in the regenerator would be H4 minus H2. 820.48 minus 595.8. So it's around 225. That's the actual maximum. Now, if you multiply that by the effectiveness specified to be 50%, we expect now 112 kilojoules per kilogram transferred. Now, because the kilogram of air is both the same for the hot as well as the cold side, you don't have a different flow rate for the hot side and cold side, so it's simpler. And so now we know that, okay, that's the actual change. Now I can finally fix X. So X is this H plus Q actual to be 112. So you get H at state 2. Likewise, H at Y is H4 minus this 112.
Okay.
Does make sense?
Yeah, and it's always going to be that because conservation.
That's right. Conservation of energy. It's adiabatic heat exchanger. What comes out of the hot goes into the cold. Now, if this changes to, let's say, 100%, well, this would change to 225. 225. If that changed to 225, then it would be 820 minus 225. Likewise, it would be that plus 225. And it would basically, this number would become 820.48, and this number would become 595.80. What I did was organize the Q's on this side plus the Q of the cycle below it, and the works right here with the work of the cycle summed below it. So the compressor is adiabatic, the turbine's adiabatic, but we do have still from 2 to 3, and I should have probably changed that 2 to 3, shouldn't I? That should be Q, not from 2 to 3, but from X to 3, right? Because that's the external heat in. So that would be this much. Let's do a quick check. It's going to be H31575.6 minus HX 708. I'm just going to put 1 there. And now that's a 5. That's a 7. That's a 6. And this is, what is it, an 8? 867.5. Check. So it is QX minus QX to 3, which is the H3 minus HX is QX to 3. That's how much heat goes in. Nothing for the turbine, and then for the heat exchanger. What we're doing here is, I should have not said 4 to 1. That's Q. Well, that's a bad looking Q. Let's put Q Y to 1. Y to 1. Let me jump back and look at that other slide, because a lot of students will mess this up. You still have a heat exchanger here, and you still have to reject some to the atmosphere. But it's from Y to 1, not from 4 to 1. Okay, and I believe the textbook, when they introduced this, they don't show this heat exchanger explicitly. They kind of just leave this out. And that's needed if you're going to look at the balance, the Q net for the cycle. So you need to include in this. Okay. And so when I add up the Q net, I have 460 kilojoules per kilogram. Let's look at the works. First of all, the works are consistent. The work of the cycle equals the net heat for the cycle. And let's take a look. Compressor requires that much. The turbine gives that much, and the difference. So when we take a look at the thermal efficiency, it's improved. It's improved significantly. It's now 53% for that pressure ratio of 11. How come it's higher than the predicted cold Brayton cycle efficiency, that analytic expression for the efficiency? Why is it even higher? It's because this was without the regenerator. This is with the regenerator. It's 53% thermally efficient. And then the backwork ratio is a whopping 40%, still higher, 39.1%. It's still very high. Okay. So hopefully all of that makes sense. Yeah. And let's click to another problem. Also, what you can do is, that problem we just solved was 50% was the value for the regenerator effectiveness. And when we came up, we calculated the thermal efficiency, what, 53%? I have to go back and look right quick. 53%, yes it was, 53%. If you decrease the regenerator effectiveness, let's say it goes to 0, what does that mean? It didn't transfer anything. If it didn't transfer anything, here's the hot side. It comes in at 4 and goes out at Y. What is the temperature at Y compared to the temperature at 4? It's the same. Likewise, if it comes in at 2 and goes out at X on the cold side, what is the temperature at X compared to the temperature? It's the same. It's as if the regenerator wasn't even there. So when you compare at 0%, that's actually no regenerator. And that's the same thermal efficiency as predicted by that equation. But you can see that this really goes up. What's that roughly? 47%? It was right here. Whoops, I read that wrong. 49.6%. Is it really 49? That doesn't look like 49.6, does it? I'll have to check that. But you can see that there's a dramatic increase as the regenerator effectiveness goes up. And that's not a small increase. You're looking at over 10% improvement. So it pays dividends to have a very good heat exchanger there. It pays great dividends. Now let's take a look at the other enhancements of intercooling and reheat. Well, let's start with a discussion of why it's so expensive to compress a gas. To understand that, you go back and you look at a pressure volume diagram, okay? And if I have an ideal gas, it's a very large specific volume. And if I want to go from this pressure to that pressure, a specified pressure ratio, I compress it. Typically, I compress it S is equal to a constant isentropically, and I'm up there. Boom. All right. This is an open system, so we're flowing through a control volume. That's the compressor. And we're coming in at state 1. We're going out at state 2 over here. And the goal is for the pressure at 2 to be high. Well, we worked out that you have to supply the work per unit mass, or W dot per M dot, work per unit mass, is equal to the integral of V dP. Now, there's a minus sign but I'm going to ignore that minus sign, but it's the magnitude of the integral V dP. As a review, you take a look from calculus and you knew how to integrate F as a function of X. You start from X of A, you go to X of B, you have some curve like that, it's the area under the curve. That's the integral of F dx, some value for that integral. Well, here, this always throws students for a loop, because what's on the x-axis? V. What's on the y-axis? P. So what they're doing is integrating dP. To help make it make sense, let me do a flip. Let me put P in the traditional X location, and let me put V in the traditional Y location. And now let's see if we can figure this out. So we start with high at state 1, it's large V, low P. There's state 1. And we're going to low V, high P. There's state 2. So there is our curve flipped. Okay. And what we're interested in is the area under the curve. Okay. And that's a visual representation of the work. Let me try and draw it like this. Lowercase w, the work per unit mass, the area under the curve. If I now have a liquid, and the liquid specific volume of the liquid compared to the specific volume of an ideal gas, what is one really large and one really small? So it's the volume occupied by a kilogram of liquid compared to the volume occupied by a kilogram of an ideal gas. Well, the volume occupied by a kilogram of liquid is much, much smaller than a volume occupied by a kilogram of ideal gas. So way down here, you may have the specific volume of a liquid. And let's say it starts at this pressure. And if I want to boost the pressure, like in a pump, it's not going to compress it, but I'll have a pressure increase. So if I compare a pump, all right, and I come in like this is now a pump, this was a compressor, and I'm undergoing the same pressure change, what I find is that work per unit mass of the pump is really small. So the work per unit mass of the pump is much smaller than the work per unit mass of a compressor. So you can see it here as well, but when you leave it in the traditional PV diagram, it's not the area under the curve, it's the area to the left. I don't see too many applications where you're looking at areas to the left of the curve, but there it is. And so you see that this work is large and this work is small for the pump. This is for the compressor right here, this work of the compressor. So as a clever engineer, you say, running that compressor is very expensive. How can I reduce that work? Well, this is if you had it compressed, ideal gas compressed isentropically. If you could compress it where the temperature doesn't change, where the temperature is constant, it actually would come out with a lower temperature at this at state 2. It would achieve the same pressure, but it would be lower because this temperature, let's say this is temperature 2 would equal to the temperature 1 if it was actually compressed isothermally. This temperature T2S is greater than T1. So the goal would be, oh, well, if you cool it as you're compressing it, it would require less work. But to have that device, usually a heat exchanger is a poor compressor, and a compressor is not a very good heat exchanger. So what they do is they say, let's do it in stages. We'll compress to this pressure level. We'll do it isentropically and then stop. Then we'll cool it back to the temperature of state 1, and then we'll compress it isentropically. And so this is now the amount of that shaded area is a visual representation of the work saved by having 2 stages of a compressor, stage 1 and stage 2, and in between cooling. So in between right here you have a intercooler. Okay, so let me do this. Let me insert a new page and say that I have a compressor stage 1 and a compressor stage 2, 2 stages to my compressor, and I bring in my fluid and I boost the pressure. But before I take it into the next stage, I put it into an intercooler, a heat exchanger, cool it off, and then put it into the second stage. From there, it's ready to go. It's ready to go. So this is the 2 stages, and this is the intercooler right there. Now, let's take a look at reheat. I'm going to do this. I'm going to show a pretty complicated system. This is a heat exchanger right here, and that's going to try to use some of the exhaust heat before you put it into, I'm going to call it burner 1. All right. Now the burner, let me sketch the whole thing out. After the burner, you put it into the first turbine stage. After the first turbine stage, you take it back out, you put it into another burner, burner 2, and then you put it into a second turbine stage. After the second turbine stage, you now try to get some heat out of it in that heat exchanger, that regenerative heat exchanger, and then you come over and you finally dispose of some energy to the environment. So we explained the intercooler. Now let's talk about, we already explained this regenerative heat exchanger. Okay. Now let's talk about why you have this burner. Well, it's metallurgical considerations. This temperature right here is some maximum temperature because your turbines materials can't take that high a temperature. Well, what they do is they bring it up to the maximum temperature, have it drop the pressure but not all the way down, then they take it back up to that maximum temperature. By burning it again, you need more oxygen in there, so you couldn't have used all the oxygen. You still have to have some oxygen, mix some more fuel, have it heated up back to the maximum temperature, and boom, there you go. What you're trying to do is bring in more heat at high temperatures, good for efficiency. All right, so that's the intercooler and basically a reheat. This is going back. We have two burners reheating. Let's put some state numbers down. You can call this state 1, state 2, state 3, state 4. I think they abandoned this X and Y at this point. It really doesn't matter. Let's call this state 5. Let's call this state 6. Let's call this state 7. Call this state 8. Call this state 9. Call this state 10. And then back to 1. I think we labeled all the states correctly, right? Let's put in a Q right here. This is Q out. This is Q in at 1. This is Q in at 2. This is Q out, IC, intercooler. So we have a Q out at the intercooler, and two Q ins, Q1 and Q2. I could put QB1 and QB2, all right? So those are our heat. How about our works? You're going to have a WT1 out, a WT2 out. You're going to have a WC2 and a WC1. So we have 4 works, 2 ins for the compressor and 2 outs for the turbine. Does that all make sense? Yeah. Now let's do this. Often you're interested in calculating, the cycle thermal efficiency, right? If you do that, I would say do this. W of the cycle divided by Q net in, or the total in. All right, well, where do we have the ins? The ins are 1 and 2. True? And then the work of the cycle would be work turbine 1 plus work turbine 2 minus work compressor 1 minus work compressor 2. Somebody says 4 terms in that numerator. Hey, why don't I do Q net of the cycle divided by Q1 plus Q2? Won't that work? Sure it will. But you just have to be careful. You won't have 4 works, but how many Q's will you have? You'll have the Q in at 1 plus the Q in at 2 plus or minus the Q out way over here that a lot of students will forget about. They'll forget about this one. Minus the Q in the intercooler. So you still have 4 terms. And you have Q1 and plus Q2. Right. So pretty good. And then each one of these you can just work out. What are they related to for a change in enthalpy? This is H2 minus H1. This is H2 minus H3. This is H4 minus H3. This is, didn't leave a lot of room there. H6 minus H5? Yeah, something like that. And then the same here, it's H8 minus H7, and this work, H6 minus H7, and this work, H8 minus H9. And I think, oops, this one over here we forgot. And that one's equal to H10 minus H1. They can have some efficiency for the first compressor stage, is isentropic efficiency. Second compressor stage, isentropic efficiency. First turbine stage, isentropic efficiency. Second turbine stage, and the regenerator effectiveness. So, wow. Right? Also, what they typically do is they specify T3 is often given. You cool it back down to something. Maybe you cool it back down as low as T1. It doesn't make sense to go below T1. And then often this Tmax is given as well. T6 and T8 are given. Let's go ahead and sketch that on a, well, maybe I can scoot down. It's going to be hard to do that though. Well, if you have a good diagram, a good sketch of it. Let's sketch it on a temperature entropy diagram. And what we have is we have the low pressure. That's a line of constant pressure. And we have the absolute high pressure. And I need to make them both steeper, sorry. Like that. And what we're going to have is an intermediate pressure over here for the compressor, and an intermediate pressure over here for the turbines. And they don't have to be the same pressures. So that's why I don't draw that line in between. Okay, but these are lines of constant pressure. We'll start off with state 1 right here. And we compress isentropically to state 2s. 2s, true? Mm-hmm. Now, this is where I even have my lines too far apart. Let's say I have some efficiency. There's 2 actual. It goes into the intercooler. It cools at constant pressure. If it cools at constant pressure, it's going to come down, and it could come down as low as that same temperature right there. Now, that would be, what state was that? 3. Now, I should have maybe left some more room over here, but I'm squeezed into this corner. I'll do the best I can. You put it through the compressor to the highest. That would be 4s. And if there are some irreversibilities, 4 actual. Now, it goes into the regenerator. And I'm just going to throw the temperature coming out of the regenerator somewhere up there. State 5. And then it goes all the way up to the maximum temperature. Maybe I don't want it up that high. Come out right there. Which is the temperature coming out of the burner, which is state 6, first burner. True? Now it expands isentropically through the first to 7Fs. But if there's some irreversibilities, there's 7 actual. We pass it back in to another burner for reheat. Then reheat brings it up to this temperature at 8, which is often the same as temperature at 6, but it's at a lower pressure. Pass it through the second turbine stage to 9s, or kick it out to 9 actual. That makes sense? And then from 9, it'll be cooled somewhere in here. I won't show it going all the way. Will be state 10, which is the outlet from the regenerative heat exchanger. And then from 10 all the way back down to 1 to close the system. So you would sketch in the Q's. This would be the Q of the intercooler, true? This from 5 to 6 is the Q burner 1. From 7 to 8, Q burner 2. And from 10 to 1, Q out. So I think those are the 4. Okay, let me take, should I scroll back up, Michael? Does that look good?
Yeah.
Those 4? Okay. Now the other thing is if you wanted to, you could sometimes show that this heat goes to that warming. So the going from 9 to 10 is a cooling in that regenerative heat exchanger, and that provides the heating from 4 to 5. So, but that's internal to the cycle. These are external. Out, out, in. And then, boy, if you put the works on there, and then it's a little more challenging too, but we could put the works on there. You have maybe a different color. What color should I try? I've used a lot of colors already, haven't I? This is a work coming in, first compressor stage, the work, second compressor stage. This is the work of the first turbine. This is the work of the second turbine.